I just clicked through in mystery box. And the problem is I forgot what that something was between last year and this year. So that's the nice thing about the mystery box in the slides, though, because it can be whatever I want it to be. So mystery box today, this limited run engagement is how do buffer overflows work? Woo! Yay! No? Not digging on it? I didn't hear wild applause. All right, so mystery box, buffer overflows. I have an example which I wrote over lunch. It's probably not in this one. Where is it? Not this one. So in my modified version of the code, you don't have to pull it up, but here's where it is. There's something called basic buffer overflow. Oh, yeah. All right, so our basic buffer overflow. In this buffer overflow, well, in this program, there is a program. It's using string to unsigned long. This is the equivalent of A to I, which we saw before, except it's an unsigned output. So whereas A to I, if you give it something with a 1 in the upper bit, right, it's going to get confused because it only wants the A to I one for negative values. It doesn't like them. So string to unsigned long says I'm going to give argv of 1. So I'm going to give some number as the first input parameter. And, I'm going to give it as a string, obviously, on the command line. And then that string to unsigned long is going to convert that into an actual number, a 32-bit value size, right? So I give a size, and I give a value. So size and value on the command line. And now I'm going to take size and value, and I'm going to pass them into lame. Lame is a subroutine. Now, we check if the return result from lame is 0, not 0 is true. So if lame is not true, print, well, call awesome, right? So if this is not lame, we will call awesome. Otherwise, we will print out, I'm so lame, in the sad face. Okay? So let's see under what condition this is not lame. All right, well, we take size, let's see, we got size, we got value, we got array 1, array 2, set that value to that, and we memcopy, and oh, we always return 1. So this is always lame. So therefore, when I run this program, it will always print out, I am so lame. There's main. Let's see if I have any parameters there already. If I do, then you need to close your eyes momentarily. Okay, good. So I need some parameters. All right, 1, 2. Don't know what the parameters are going to be yet. Pass in 1, 2. Oh, why are you dying? It's got to be hex. X2. So this string to unsigned long, it's saying treat the second number as a base 16 number. So I have to put 0x to say it's going to be 16. Try that again. That sucks. Why is it dying on that? I'm so lame. I don't think that's going to make a difference. Oh, well, this is release, and that's like a terrible idea. Wait, does it have to be optimized? I think that's right. Well, let's see. I am so lame. Can't even get my own example to work. That makes no sense to me. To the disassembly. Well, the thing which strikes me right here is, I'm doing a call, but I'm not like cleaning up the parameters to the call. So I'm wondering if I like screwed with this and set it to standard call or something like that.
Hey, Zeno, this is Greg. When I built it, I was getting warnings about string unsigned long being undefined, so it's assuming that it returns an int. So I don't know if you're getting the same warnings, or if you have to include something else.
Question. That could be it. Let's try rebuilding it. Yeah, so string unsigned long is being considered undefined.
I need, I think, a STD lib as well.
Standard lib as well? Compiled everything. Built just that. Well, now it's saying I have it, but it has like a different definition. But that may be good enough. So let's see here. No. All right, we're going to come back to this. I have no idea what changed. All right. Now we have to go back to lecturing, and this is going to be such a disappointment compared to seeing the buffer overflow example. All right. Soldier on. So, messing with the disassembler. Whereby messing with, I mean causing a disassembler to actually give you the wrong sort of output. So this is this is talking about an academic paper actually from around 2003. And so this Lin and Debray paper, they were talking about how you can obfuscate an executable so that static disassembly is going to fail on it, basically. So in the paper, they compare and contrast two types of ways that you can disassemble. So there's the obj dump kind of way, where you start at the beginning and you basically go top to bottom and you just disassemble bytes in the order that you see them, subject to some, trying to figure out where functions start. So you see a function, you start, you disassemble top to bottom. On the other hand, there's recursive traversal disassembly, which is what IDA does. So in recursive traversal disassembly, what you would do is you would start at the beginning of the program, you would go along and you would disassemble instructions until you see your first sort of control flow changing instruction. So if I see a call instruction, I go to the target of the call, I disassemble everything there until maybe I see a jump instruction, and then I go to the target of the jump, and so I just keep recursing down. Every time I see a branch, I take that branch, and I go to that target, and I disassemble code at that target. When I eventually see something which, goes back like a return instruction, either I see a return instruction or like maybe it just falls off the end and it's, well, typically you're going to see a return instruction. But when I see something that indicates this thing is done disassembling over here, for instance, let's say you have, a blob of code here. This is your first chunk of code. And, this has like a, jump to code 2. Code 2. Wow, it's terrible. Jump to code 2, right? And so that may tell you that we're going to go down here, and you know this is code 2. Right, and it's going to go along and disassemble this. And so where this may stop, it may stop in that there may be like a jump to up here, and then this disassembles until like this hits something where you've already disassembled, right? And so if you start disassembling here, you get to here and you say, well, I already disassembled this in code 1, then this descent is done, and you go back up a level, and you go back down here, and then you start disassembling right here, right? So basically the point is you just, every time you see something which is targeting somewhere else, you go to that target until you get to some termination condition, whether it's a return instruction or like you've hit some code that you've already disassembled, and then you recurse back out. Yes?
So when you say some code that you've already disassembled, couldn't I potentially, albeit it's probably headache-inducing, offset by a byte or two and jump to something which, when you start a couple of bytes offset, gives you a completely different interpretation of that code we've already disassembled?
Yes, you could do that. But what the disassembler will basically do is it'll go with, typically, I mean, they can do it one way or the other, but whatever way the disassembler chooses to do it, right? So she said, what if, you know, I jump from here into there, for instance, or, well, I went from there, and then maybe I went down to, you know, here or something like that. Wherever you go, if you try to target into some code which the disassembler has already disassembled, they can either say, no, I will not print my new interpretation of that code, because this is just flat disassembly now. This is not like running a debugger. This is just, I'm going to give you a list of what I think the instructions are. So it can either say, A, no, I consider that an invalid target, and it'll just print out the first interpretation. Or B, it can say, yes, I consider that a valid target, and then it'll print out that interpretation of the overlapped thing. And so therefore, this could then be some different code, and there could be like some region of ambiguity in there where like, you know, this first instruction got cut in half, right? And therefore, it maybe needs to back that out and say, well, I don't consider that a full instruction anymore. I consider that 2 data bytes, and then the subsequent interpretation. So it's really just disassembler can decide how it wants to do it. It can either choose to allow the overwriting of its first notion of code, or it can say, no, I will never overwrite my first notion of code. All right. And so, you know, this paper also talked about sort of this, quote, self-repairing notion of x86 assembly. So when we saw that offsetting the bytes by a couple of bytes each time, we got a slightly different description of the disassembly. But eventually, it would sync back up, right? When we were in GDB, eventually we would get like this, we would get that pop EBP, or when we saw everything like so, right? Even if I offset by some number of bytes, eventually the stuff seems to always sync back up at this call instruction, or, you know, somewhere else later on we get back to the original interpretation. So this Lin and Debray paper sort of recognized that fact that while you may be able to like get a disassembler to start disassembly at the wrong location, right? So let's say you tricked the disassembler into disassembling start at, you know, 386 rather than 385, right? And you got it to print this sequence out. The thing is, you would have only screwed up the disassembler for 3 instructions here, right? So if the human's looking through there, the human may have been like, saw that junk, and, you know, he may have thought something wrong. But eventually, it's going to self-synchronize again, and it's going to get back to the correct thing. So just messing with it one time does not guarantee like everything's messed up. It just kind of says for some small area after that, potentially there's the ability, potentially the disassembly is going to be messed up, but it may eventually become fixed again. So that has no guarantee that if the analyst looking at the code somewhere else, that region somewhere else may not be screwed up. So there was a number of different types of things that they said, here's things we can do to modify our assembly in order to make it so that different disassemblers kind of choke on it and give the wrong output. So in the case of the linear sweep type things, so this was recursive descent traversal, right? Recursive traversal. In the case of linear sweep, there's a very simple sort of thing you can do. If the code is going down, so I said that, linear sweep, it's going to assume here's one instruction, then here's the next instruction, then here's the next instruction. And so if we have something like, this one sucks. Oh, that's why why my fingers are all dirty. So let's say I have push EAX, and then call, blah. And then, we assume that, so here's the thing, a linear disassembler assumes that one path here is to call blah, and then it assumes that the blah is going to return immediately to the instruction after call, right? Because call pushes the address of the instruction after call. So obviously the code that's going to be well behaved is always going to return to the instruction immediately after call. So it's going to take the byte immediately after call, and it's going to disassemble it, and maybe it's going to get add ESP or something like that, right? So that's kind of how linear traversal says. It says when I have somewhere where control flow diverges, I will assume that I will do this first, and then later on, I'll maybe go back and find out where the call is, and maybe I'll disassemble that if I didn't disassemble it otherwise. Probably not, actually, since this is linear. Right, it just goes top to bottom, and if blah isn't in our code, then oh well. If blah is in our code, well, then presumably it should get hit eventually because we're trying to disassemble all the bytes in our code. So an example of something you can do, well, that's one example. And then, another example may be something like this. Compare, what was it, EDI and 3. We saw that earlier, right? Jump below target, right? And then if this jump doesn't, if this condition below doesn't hold, then we fall through to the next instruction, right? I don't know. So here's the other thing, right? So linear top to bottom thing is going to say, well, yes, I'm going to always, disassemble the next byte after the conditional thing because either it's going to go to the condition or it's going to fall through, and the next byte immediately after a conditional jump should always still be valid because it's going to go one way or the other. There is the possibility that it's going to fall through, and therefore this has to be a valid instruction at the end. So, what is the literally unconditional jump? Yeah. Okay. And then a third form. Right, so I don't know what EBX is here, but, so we may have an unconditional jump, but again, the thing is, this is definitely going somewhere else, right? You have no reason to believe that the next byte is necessarily an instruction, but in practice, right, all of these instructions get put next to each other. So probably, unless this is the end of file, there's probably another instruction here, and maybe this thing jumps down, but maybe it was like that for loop, right? So maybe you jumped down somewhere, and then you jump back up somewhere else. So the linear disassembler doesn't care. It just goes top to bottom and says whatever's coming next, I'm going to put an instruction. I'm going to treat that like an instruction and write that out. So whatever that will say. Push, whatever it is. Okay. So here's how you can mess with obj dump moving down. So, and I'll say that generally speaking, these sort of obfuscations are assumed to take place post legitimate compile. So you have some binary, you've compiled a binary, you've disassembled that binary, and you want to now obfuscate it. So you've got a binary which disassembles correctly, and you want to make it disassemble incorrectly. So what you do is you pull apart your binary, potentially, instruction by instruction, and you find places where you have control flow changes. And you know that no matter what, the linear descent disassembler is always going to assume that the next byte sequence immediately following some control flow change can still potentially be legitimate. So what you do is you slice this apart, you pull apart these instructions. Let's make it something like this one right here, right? This is a good example where, yeah, you can see it's a call instruction. Probably the next instruction is going to be legitimate. Well, so there's a couple of ways you could do this. One, you could modify blah so that blah doesn't return directly to the thing which was pushed. It could like take that address and then like add 4 to it or something. And then it could actually return, when this blah returns, it could actually return to right here. And so then these 4 bytes would never actually be executed, right? Call would call somewhere else, and when it returns, it would return to right here. And so these 4 bytes would never be executed. So you could put in whatever you want for bytes right here. And if you put, say, like, you know, so you take it apart and you put it back together where this instruction, the add ESP plus 4, gets put down here. Right? And so then there's this gap right here of 4 bytes. And what you could do is you could put something in here like maybe a 5-byte instruction, right? So you know that I'm going to do an instruction, and this instruction is defined by 5 bytes. So I'll say maybe it's like E8. This is like actually another call, like that's a prefix for a call instruction. You don't need to know that, right? But an E8 plus 4 bytes can be like an offset, like say a 32-bit offset, right? But I can't fit 4 bytes right here, so I'm going to put 3 bytes right here. And remember, these bytes right here are never actually executed. So I'm going to put like, you know, some offset in little endian order. I'll say 1, 2, 3, 4, I don't know, 4, 0, something like that. And so the thing is, when the disassembler comes along, it saw the call instruction, it disassembles the call instruction. It gets to the next byte immediately after the call instruction, and it assumes that that byte is something which can actually be executed. But there's nothing to say just to a disassembler that byte will ever get executed. I can modify things so that it never gets executed as an instruction. Disassembler doesn't know that. It says, aha, E8, that's a call instruction. Now I will take 4 bytes. So it's going to like grab a byte from this next instruction. So it's going to take another 4 bytes right here. One of the bytes, the first byte for that add instruction is going to be, you know, merged into the disassembled output for what this call instruction's address is, right? Because we had a 4-byte address, got to get those 4 bytes from the next 4 bytes. So one of those bytes came out here, and then now it's going to start at the next byte after that. And so in the middle of this byte, whatever happens to be, in the middle of this instruction, whatever this byte happens to be, it's going to say, now I'm going to interpret that as some instruction. Right? And then I'm going to interpret that as some instruction, right? And these are contiguous instructions one after another. Right? So, and then it goes down. So by playing this sort of game where you make it so that something immediately after a control flow is not actually ever used, the disassembler doesn't know that. So it always starts right here, starts disassembling. You know, like I said, this can be a 5-byte instruction. It can be a 2-byte instruction, and then, you know, a 3-byte instruction. A 4-byte instruction, well, a 3-byte instruction, then a 5-byte instruction, right? And the point is, this may be the legitimate instruction in which you're trying to hide from the analyst, right? So the analyst wants to see push, call, add, right? That's what the original compiled code did. But you pulled the code apart at the instruction level, and you put it back together in a way where there's maybe some junk in between instructions, but you've made sure that that junk never gets executed as an instruction. It's just there so that when a disassembler comes along and hits it, it disassembles it incorrectly. So that was one example where I said, you know, you could pull this apart and you could maybe modify it so that, you know, if you're pulling everything, you know, if you're going to take things apart at the assembly level and put them back together, you can do arbitrary functionality, right? So I could go to blah, and like right before blah does a return or something like that, I could do like add 4 to, you know, EBP plus 4. Something like that, right? And that would make that saved EIP be 4 bytes lower so that when I return, you know, it goes to a different location than immediately following the stack. So that's one way. Another way that you can do things is you could take a conditional statement like this, right? And it says jump below, and you could make this functionally unconditional. So you can say, I'm going to put some sort of compare before it where I know what the input parameters are, and I will never, ever not take the jump, right? So the simple example, right, is I could do a jump 0. Right? It says jump if the 0 flag is set. And then I could do like, compare 1, 2, right? So is 1 minus 2, 0? No. This jump 0 will never be taken now, right? So it'll always go this way and then, well, sorry, that's for screwing up recursive descent things potentially. Jump if not 0, right? So this result will never be 0. This will always take this jump if not 0 kind of thing, right? And therefore, whatever I put here, the disassembler is going to disassemble that, but there's no reason to believe that I will actually ever execute that. So therefore, that can put some instruction stream, and I can then again, put some offset down here so that this junk byte gets grabbing a chunk of some other legitimate byte, which I would have had otherwise. So this is one way that you can mess with the disassembler, essentially. You can force bytes in here. That's going to alter the interpretation of this because no longer is the first byte going to be something which says I'm an add. That first byte's going to get added into this as far as the disassembler is concerned. And then the next byte will be some other instruction.